You guys look at any homework, any problems that I can do for you? How's the derivatives going? Practice with the definition of derivative at all?
Yeah, it's pretty easy.
Okay, so far?
I have a couple questions.
Sure.
Like 25 and 27, I just didn't really get what it's asking to do. We said the limit process. I don't understand what the point of the limit is.
An exercise find the equation of the tangent line to the graph of f at a given point, and then use the graphing utility.
Basically, just make a graph.
Well, okay, so let's look at 25. So they give you the function x squared plus 3, then they give you the point negative 1, 4. So this is number 25. So, let me walk you through this real quick because it'll be good review if nothing else. So, the instructions say find the equation of the tangent line to the graph of f. The problem is, when you find the derivative using your limit process, what does that give you? Do you remember? Does it give you the equation of the tangent line? It only gives you the slope of the tangent line. So there's an extra step after you actually do the derivative here involving this point. Okay, so let's go ahead and do the derivative just as a reminder of how it works. So how would we find f prime of x here? Limit of what?
X plus a of x minus.
Right, so you do the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So this is the limit definition of derivative. This is what all we know right now. In this particular case, this is our f of x. So we have to plug x plus delta x into this guy. That's step 1. So over here, we'll get the limit as delta x goes to 0 of x plus delta x squared plus 3. All right, you just replace this x with this x. Minus the function again. So minus the entire thing, x squared plus 3, all over delta x.
Bless you.
That's it. Remember, hopefully you guys are good at this still. When you square a binomial here, what do you get?
X squared plus x
Oh, good. We got to work on your unity, but sound like you know it. So when you square this binomial, you get x squared plus 2x delta x plus delta x squared. Don't forget your plus 3. Minus, this whole thing has to get minus, so we distribute it. Minus x squared minus 3 over delta x. Limit is delta x goes to 3. Canceling happens, hopefully. Gone, 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 gone. So end up with the limit. Delta x goes to 0. 2x delta x plus delta x squared over delta x. Everything else went away. And how do you finish this off?
Delta x
Factor, right? There's a delta x on top, so you can pull out a delta x, pull out the greatest common factor. And then you write the leftover in parentheses. You have a 2x left over and a delta x left over. Limit 0. Now that this is multiplication, these guys can cross off, giving you a 1. And then you can go ahead and apply your delta x going to 0 now that the denominator is gone. So all we're left with is 2x. And if the problem said find the derivative of the function, this would be your answer. Okay. But it didn't. It said find the equation of the tangent line to the function through this point. So what I found here is a formula for the slope of the tangent line at different x values. But all I really care about is what happens at the point negative 1, 4. Okay, so I'm going to go ahead and plug what in order to get the right slope? Negative 1. Right, this is my given x value. So then I can calculate the slope at x equals negative 1 by doing f prime of negative 1. So plug negative 1 into here. 2 times negative 1.
Equals 4. Oh, sorry.
What's that?
No.
Okay. So this is the slope of my function, the slope of my tangent line at x equals negative 1. But that's still not everything, because it asks for the equation of the tangent line. Yeah, so now you got to go back to your old algebra formulas, because they want the equation of the line that goes through this point, right? So think about this as x1, y1, and this slope. So you can either use y minus y1 equals m times x minus x1. Right, that'll get you the equation of the tangent line. Or if you want, you can use y equals mx plus b. Either one of these should be able to get you the equation of the tangent line. Let's use this one right now. So to finish this off, I would plug in negative 1 for x1, 4 for y1, and negative 2 for n. So the equation of my tangent line will be y minus 4 equals negative 2 times x minus negative 1 will be plus 1. I'll probably clean this up because it's ugly. Distribute out the negative 2 and add 4. So this is the equation of the tangent line at negative 1, 4. By the way, if you happen to use this formula, do you remember how to use this one to find the equation of the line?
Yeah.
Without using. So if you're going to use this one, you have to solve for b. So if you don't like this formula and you like this formula, then you would say, okay, well I know m is negative 2, and I know when x is negative 1, y is 4, then I can solve for b. Right, this is 4 equals 2 plus b, so b has to equal 2. Then you plug back in here to your original formula, y equals negative 2, because slope is negative 2, plus 2, because that's b. Either way, we should get the same b. So be careful, if it asks for the slope of the tangent line, then you can just plug in your x value. Plug your x value into your derivative, that'll give you the slope of the tangent. But if it asks for the equation of the tangent line, you gotta go one step further and make your equation from using your 96 or 96 or wherever you're doing this. And then, hopefully just so you can kind of put this all together. What this looks like you guys know what the function actually looks like here, x squared plus 3? It's an upward parabola because it's a positive x squared shifted up 3. So this is our function. What this equation is saying is if I find the tangent line going through negative 1, 4, so negative 1, 4 would be up here. If I find the tangent line going through this point, which is this guy, this line should have the equation y equals negative 2x plus 2. So it goes through y-intercept of 2 with a slope of negative. I don't know, what do you think? What else? What else is giving you problems?
Can I have my test, please?
Can you have your test, please? Can you wait until I'm done?
Yes,
It's in my bag.
No, just.
Yeah, if you guys didn't get your test last time, ask me afterward. Or if you need a, if you came in late and you need a take-home test, or take-home quiz, ask me afterward.
Sure.
Well, if you don't have anything else, I'm gonna ask you questions. Anything else from 2.1 you want me to go over, or should I just give you some problems to think about? So one example I didn't get to last time. So kind of a review from last time. Suppose I give you this guy. F of x equals 1 over x. I want you to find f prime of x. What do you do? Same thing that you just did, except now it's an ugly fraction, so you're going to have some algebra to deal with. Right? But you start the same way. Whenever you're finding a derivative in this section, you start with your limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Right? This is your definition of derivative. So this will equal f prime of x. But now when you do x plus delta x and you plug it into your function, you end up with a fraction. So this will equal the limit as delta x goes to 0 of 1 over x plus delta x minus 1 over x, right, because you minus the function again, all over delta x.
What if you moved it to x to the negative first? Would that be easier?
X to the negative 1.
Yeah.
Then you would have x plus delta x to the negative 1. And you still have, I mean, you're going to have to make it a fraction to combine these. Like, there's no way of getting around common denominators that I know of here. So it actually wouldn't help at all. For this particular case. In the next section, when we do the power rule, then you're going to want to do that. But when you're doing the definition of derivative, it doesn't help you to make this a negative common denominator, as far as I know. But what do we do to get a common denominator here? What's this first guy get multiplied by?
X.
Right, he needs an x factor. So you do x on top, x on bottom. And this guy needs this whole thing, right? So you do x plus delta x, x plus delta x, and then hope something magical happens. Isn't that how you guys spend your lives? Sitting around hoping something magical happens. Limit as delta x goes to 0. This guy is going to give you an x on top. So x over, I wouldn't multiply out the denominator. There's just no need. Minus the entire fraction x plus delta x over x times x plus delta x. All over delta. Now, you have to be a little bit careful here because this negative is going to go to both of those. So you got to watch that. That's a common mistake. So this ends up being a limit as delta x goes to 0. X minus x, the x is just drop off. But then you have a negative delta x left over. On the bottom, it's just the common denominator. And delta x way down below. How does it simplify?
negative 1 over x times x plus delta.
So make this guy delta x over 1, right? And then flip him up. So this will end up equaling the limit. Delta x goes to 0. Keep this guy the same. Negative delta x over x times x plus delta x times 1 over delta x. And now you have a delta x on top, delta x on bottom.
Look at it.
Right now that our delta x factor is gone on the bottom, we can just put in 0 for delta x. I'm running out of space, I'm just going to do it right here. All right, put in 0 for delta x here, and count what you're left with. On top you have 1. On bottom you have x squared. What else did I forget?
Negative.
So we have negative 1 over x squared altogether. That's your derivative here. So when you're dealing with rational functions, with functions that have denominators, and you're doing this definition, you gotta get common denominators. So that's one. Quick questions. That's okay? We're good with that? Because I pounded limits into you so well. Go ahead.
So this will always be true. Like if we get it in another exercise, they give an f the x as 1 over x,
This will still be the answer, yeah.
it still be the answer. So
So today we're going to get, like I said, today we're going to get a nice rule that allows us to cut straight to this because there's a pattern on a lot of these. So we're going to extract the pattern.
Growing up.
Now, the other thing I wanted to review was graphs. More specifically, how the graphs of the derivative and the graphs of the original, the graph of the derivative and the graph of the original function relate. So, here's an example. Sketch a possible graph of y equals f prime of x. I'm going to give you, I don't know. I'll give you the original function. Let's make it 1, 2, 1, 2, 3, upside down parabola. So here's your original function, f of x. Question is, how can we go from the graph of this f to the graph of f prime, the derivative? What kind of things do you look for?
There's e flat on top.
Yeah.
0.
So one sort of critical point that helps you really get an idea of what the derivative is going to look like is finding where you have a horizontal tangent line. Finding where the slope of the tangent line equals 0. So these turning around points here, if you drew a tangent line, the slope of that tangent line would be 0. So what that means is that this corresponding x value, on the derivative graph, your y value is going to be 0. So over here on the derivative graph, since I had a slope of 0 at x equals negative 2, I'll put a point at 0 when x is negative 2. And then you kind of have to analyze what the slope is on the left of that and what the slope is on the right of that. So on the left, does this slope look like it's positive or negative? Positive, it's going up. Right? If you're walking from left to right, you'd be going up. So this is a positive slope. What if you go further to the left? Is this more positive or less positive?
More positive.
It's steeper. So this is more positive. 2 plus whatever that means. On this side, n is now negative because you're going down. And this is even more negative. So what's happening is, since your slope is positive on the left of negative 2, you're going to have a positive y value over here. And it's going to keep getting more and more positive as you go to the left. On the right, your slope is negative, and it keeps getting more and more negative as you go to the right. Now, I haven't, so this is a possible graph of the derivative. I haven't marked where this y-intercept is. How would I calculate, how would I figure that out?
What? X equals 0.
So I don't actually have any equations, so I would have to rely on this graph. So what would I look at in this graph to figure out this y-intercept?
What? X equals 0.
Where x is 0.
When x is 0, what do I focus on?
The y value. Oh, never mind.
Slope.
Slope. But I would have to actually, if I had a decent enough graph, I might be able to estimate the slope here. Maybe I could say, oh, this is -5. And this y value would be -5. My graph's kind of crappy, so I can't really estimate the slope. I mean, there's no other points anywhere. But my point, my sort of main idea here is that if I actually want to know what this is, what this point on the derivative is, I would need to find the slope of the original graph at x equals 0. Not just the y value. Okay. What do you think about that analysis? Could you go backward?
Yeah.
What if I gave you the derivative and asked for the original function? So, I want to sketch a graph of that. Possible graph of that. But what I'm going to give you now this time is instead of the original function, I'm going to give you the derivative. So maybe our derivative looks like, like this. So this is now y equals f prime of x. Backward into f. What kind of things are we going to focus on here?
Either quadratic, or
So-
it'd be a cubic,
Yeah, I guess, but that doesn't really matter.
so it would be
I know it crosses
negative
0.
slope on the left side.
Right, so focus on the, so, you know, the derivative here, the y values are giving you the slope over here, so we're going backward. Specifically, this guy has a 0 y value, which means you're going to have on the original graph a horizontal tangent line, a 0 slope. So this means n equals 0 on the original graph. So n equals 0 on the original graph of f. Same thing over here. Everywhere in between you have negative y values. So your slope is going to have to be negative. Your function is going to have to be decreasing on this interval. Since all of these y values are negative, you know in here, slope is negative. And then on the outside, on this side, all of my y values are positive, so my slope is going to be positive. My derivative is bigger than 0. You don't really have enough information to say at all where the graph is, because all you have is information about slope. Right? You can't tell me whether this curve is way up at 100 or down at that negative 1,000. Okay? But you can kind of give me, if you pick sort of a starting point, you can give me a good idea of the shape. So at -2, I'm going to have a horizontal tangent line. So this guy is going to be a horizontal tangent line. Before that, my slope is positive, which means I must be coming up like this. And then I turn around because I have a horizontal tangent line there. And then the next time I turn around again is at -2. Oh, I don't know. Let's make it very symmetric. I'm sorry, the next time I turn around again is at +2, not -2. So my slope is negative in this interval, and it keeps going negative until it gets here, and then it turns back around. It becomes positive. So this is a possible function, original function for this derivative. Okay, so I'll let you internalize that for a second. Questions?
Questions I just want to ask.
Why do I know that the slope is positive on the derivative graph again?
So this graph, the y, you should think of the y-axis here. Any y value for this graph, y values are the slope of f. Slope of the original function. So like, for example, if you look at this point up here, on the derivative graph, the y value is positive. Y value being positive tells you that the slope of the original function is positive. So once you cross down here, you have negative y values. And so that points to the original function having a negative slope going down. And then it crosses back up to positive. So that's how you know the original function has a positive slope. After 2.